Okay, so now we're on to induction machines, really meaning induction motors, because we already covered. There's other videos that cover how to do a three-phase voltage system and the distributed windings. Now we want to put all these pieces together in order to look at induction machines. So first of all, we're going to start by watching a YouTube video that provides a good overview of an induction motor.
Induction motors are the most commonly used electrical machines. They are cheaper, rugged, and easier to maintain compared to other alternatives. In this video, we will learn the working of a three-phase squirrel cage induction motor. It has two main parts, stator and rotor. Stator is a stationary part, and rotor is the rotating part. Stator is made by stacking thin-slotted, highly permeable steel laminations inside a steel or cast iron frame. Winding passes through slots of stator. When a three-phase AC current passes through it, something very interesting happens. It produces a rotating magnetic field. To understand this phenomenon much better, consider a simplified three-phase winding with just three coils. A wire carrying current produces magnetic field around it. Now, for this special arrangement, magnetic field produced by three-phase AC current will be as shown at a particular instant. With variation in AC current, magnetic field takes a different orientation as shown. From these three positions, it's clear that it's like a magnetic field of uniform strength rotating. The speed of rotation of a magnetic field is known as synchronous speed. Assume you're putting a closed conductor inside it. Since the magnetic field is fluctuating, an EMF will be induced in the loop according to Faraday's law. The EMF will produce a current through the loop. So, the situation has become like a current-carrying loop is situated in a magnetic field. This will produce magnetic force in loop, according to Lorentz law. So, the loop will start rotating. A similar phenomenon happens inside an induction motor also. Here, instead of a simple loop, something very similar to a squirrel cage is used. Three-phase AC current passing through stator winding produces a rotating magnetic field. So, as in the previous case, current will be induced in bars of squirrel cage, which is shortened by end rings, and will start rotating. That's why it's called an induction motor. Electricity is inducted in the rotor by magnetic induction rather than direct electric connection. To aid such electromagnetic induction, insulated iron core lamina are packed inside the rotor. Such small slices of iron make sure that eddy current losses are minimum. This is another big advantage of a three-phase induction motor. It is inherently self-starting. So, you can see here that both magnetic field and rotor are rotating. But at what speed will the rotor rotate? To obtain this answer, let's consider different cases. Consider a case where the rotor speed is the same as the magnetic field speed. Since both are rotating at the same speed, the rotating loop will always experience constant magnetic field. So, there won't be any induced EMF and current. This means zero force on rotor bars. So, the rotors will gradually slow down. But as it slows down, rotor loops will experience a varying magnetic field. So, induced current and force will rise again. And the rotor will speed up. In short, the rotor will never be able to catch up with the speed of the magnetic field. It rotates at a specific speed, which is slightly less than synchronous speed. The difference between synchronous and rotor speed is known as slip. Rotational mechanical power is transferred through a power shaft. In short, in an induction motor, electrical energy is entered via stator and output from motor. Mechanical rotation is received from rotor. Energy loss during motor operation is dissipated as heat. So, a fan at the other end helps in cooling down the motor. Hope you got a good introduction on the working of induction motors. Thank you.
Okay, so let's kind of review what we learned from that video. So first of all, the purpose of the stator is to create this rotating magnetic field. And that's possible because we have a 3 sinusoidal of varying windings and we have a 3 phase of voltage applied to the windings. We also see that the rotor is just a wire loop set up in a squirrel cage that's filled with high permeability material so that we don't lose a lot of our magnetic flux. And essentially it's just a big chunk of metal, so there's nothing to break apart. There's no physical connections between the stator and the rotor, no brushes, and the varying magnetic field produces the force. So it's a very robust motor because there aren't all these connections, mechanical connections that will break. Okay, so now let's go into details. So let's kind of review the basic structure again. So we basically see here is our stator that basically has all these distributed windings all the way around here that we talked about before, and it creates a rotating magnetic field. So here over on this side here is our rotor. And so you can kind of see with the rotor, it basically has what's called this squirrel cage. So I have these conducting bars that are connected across, and then all of those are shorted together with these end rings. And then, as you can kind of see in this picture over here, these are the conductors along here, and then it's filled with these high permeability magnetic materials so that we get a very small air gap and we get a high magnetic flux density. Here's another picture kind of showing a squirrel cage. And you can see this one is using copper. It says copper or aluminum bars, but it kind of shows these copper bars that are slotted into this iron core material. And there's no electrical connection between these materials and the iron core. So the induced current is only going to be in these bars, and we want to limit the amount of current that's induced in the magnetic core. Okay, so let's look at Faraday's law to kind of review all this. Like we did with the DC motors, we basically have an induced voltage, which is related to the speed of the wire loop crossed with the magnetic field. And then we also induce force on current carrying wires, which is basically the current times the wire crossed with the magnetic flux density. Okay, so let's start with the induced voltage. So what we see here is that the magnetic field is rotating across here, and it's rotating at synchronous speed. Okay, and then that's going to induce the rotor to be the rotor to be rotating around this direction. So if we're looking at the speed of the loop relative to the magnetic field, you see that effectively the omega synchronous is going to be greater than my motor, which means that the magnetic field is moving faster than these bars. So that kind of really means that the bars are moving kind of counterclockwise if we use the magnetic field as the frame of reference. So then what we see, then we get this equation right here, which is related to the slip speed. So the faster the slip speed is, remember that the slip speed is the synchronous speed minus the motor speed, times the kind of the size of my loops, and then we have this cosine of theta. And so the cosine of theta is because if I look right here, this one right here is perpendicular. So my effective speed is to the left, which is perpendicular to my magnetic field. Over here, you see that my speed is down here, okay? But my magnetic field is down, so this one isn't going to induce a voltage because my speed is parallel to my magnetic field. Because remember that the magnetic field isn't just here, it's that direction, but basically everywhere across this kind of uniform spread across there. Okay, so now what we're going to do is right here, we're taking the bars of my squirrel cage that are rotated around, and we're basically unwrapping them. So we see that we have a short at the two ends, so this is the front and the back slip ring. And then we induce voltages on these, and they have a little bit of resistance. So this is the resistance of the bars. And so then what we see down here is that the induced voltage on the bars caused by Faraday's law is going to create a current. And so the current is going to be related to the induced voltage. So this part on the top is the induced voltage divided by the resistance. And so we create these currents, and they're going to be sinusoidal currents because we get a sinusoidal variation in my induced voltage. Okay, so now let's look about the electromagnetic torque. So our force is going to be equal to the current times the length of those wires in that loop crossed with my magnetic field that's produced by the stator. So we see that the induced torque is going to be has some coefficient here that's going to be related to the fact that I have a whole bunch of bars that I have to add up and all of that. So we add up all of these different bars times my induced magnetic flux density times the induced current in the rotors. So we see that it's basically some coefficient times my magnetic flux times my current. Well, my current is also induced by the magnetic field. So this is the induced current in the rotor is going to be proportional to the magnetic field and the slip speed. So now I can take this and this right here, and I'm going to plug it in right there. So now I have basically the electromagnetic torque is going to be some coefficient times the slip speed. So when we're all done, we see that my induced torque is proportional to the slip speed. And we're typically going to measure that proportionality constant just for the system rather than going through it all. But you can kind of see that it's strongly related to the magnetic flux density. So the higher we can make our magnetic flux density, the more torque we're going to get relative to the speed. So that's why we want to have a high magnetic flux density, which means that we want to have a small air gap to keep our magnetic flux density high. Okay, so now that we have the basic concepts of the induction motor all set up, now we want to develop an equivalent circuit for our model, just like we did for the DC motor. We're going to find out that the equivalent circuit is going to be more complicated than it was for the DC motor, but we still need to go through and do it. So I broke this down into steps. So the first step you can see here is we need the equivalent circuit for the stator. So we're going to start with the stator, find its equivalent circuit. And that's kind of what they call an open circuit rotor. Okay, so the rotor isn't affecting the stator back. And then we found out that we get this inductive coupling from the stator magnetic field over to the rotor. So the rotor is we're going to get an induced voltage and induced torque into the rotor. So we're essentially modeling this as a transformer. So we get this inductive coupling from the stator over to the rotor, which is going to affect the current on the stator. So it's basically just a transformer. And then we're going to reflect the rotor part of the transformer over to the stator side so that we have a simple combined circuit that combines both the stator and the rotor and not have to worry about the transformer part. And then we can see that we're going to calculate the torque from the mechanical power. So we're going to have this big circuit and we're going to look at what the mechanical power is and get the torque from the power rather than the torque from the current like we did with DC motors. So we're going to do in a power sense instead of current. Okay, so let's start with the stator. So the main part of the stator, it's basically just a sinusoidal winding. So we can just treat it as, so the main component of the stator is going to be an inductance. And you see over here that we basically, the inductor is basically a Y-connected inductor. So each of the phases has its own inductance. So we're going through some quick derivations. We're not going to go through all this in too much detail, but we basically see that the induced voltage is going to be related times some magnetizing inductance times the derivative of the current that's going through the line. So let's start by looking at a single line, and we're doing that by just saying that the current through the B and the C windings are 0. So from before, we calculated that our magnetic flux density of the stator is basically given by this equation here. Now, before, when we did it, we calculated our inductance of the flux linkage, which is N times my magnetic flux times my area divided by my current. We can't use this in this case because B is not constant, and area and the inductance can't vary with the angle even if our B is. So we can't use this simple method, so we're going to move over to a stored energy method. So the stored energy in an inductor is equal to 1/2 Li squared. You probably remember that from 240. You can also figure out how much stored energy you have in a magnetic field. So that's this part here, which is if I have a known magnetic field and a known permeability, then we can basically, this is another equation for the stored energy. Well, now that I have these two equal, I just solve this for L, and I get this equation right here. So then we just have to plug in our magnetic field, magnetic flux density, our permeability, and the current to calculate what the inductance is. So from before, we have the magnetic flux density is 0 everywhere except in the air gap, because we're assuming that the relative permeability of the metal is much, much higher than the air. So this is our magnetic field right here. And then we just have to integrate over our magnetic field. And the only part of this that varies with position is the cosine of the angle. So we pull everything else out in front except for this little integral, and then we basically integrate this over our volume, which is right here, going to cylindrical coordinates, do this integral we get here, and then we are all done. This is our inductance for a single phase. Now, we also get mutual inductance caused by the other windings. And so in order to do all this, we can kind of look at some of the okay, so we have this is our inductance that was this inductance right here. I guess this was repeated. And then we have some mutual inductance caused by the other windings. And so we get a little bit more inductance. That's this 3/2. And so then this is our inductance for a single phase, taking into account all three phases kind of all coupled on top of each other. Okay, so now here is the equivalent circuit of our stator. So this was the inductance that we just calculated. The RC is our core loss. So that's our eddy currents, hysteresis, that we had before. We have the resistance of our stator windings, and then we have the stray inductance. So you see that this is very similar to what we had when we did the non-ideal transformer model. It also looked like this. And remember that this is the single phase equivalent of our induction motor stator. Because remember that there are 3 of these because we have a 3-phase Y-connected stator. But we're typically going to do a single phase equivalent and then multiply it times 3 to get our total power. Okay, so now we're going on to the rotor equivalent circuit. So what we see here is we have the same effect. So here is our stray inductance that we have. And then here is our rotor, and this is the rotor resistance. But everything is related to the induced voltage across here is related to the slip. So up here you can kind of see that this is the equation for my slip. So it's basically the ratio between the synchronous speed and the motor speed. And that's called the slip, or the slip speed. And you see that our induced voltage, our induced EMF across there is going to be related to the slip speed. And the slip speed is also going to determine our inductance. So this is the model, the single phase equivalent model for our rotor that has this induced piece across there. Now, you can see that this induced voltage here is going to create a current. So the induced current right here is going to be the induced voltage divided by the total impedance. Now it'd be easier to divide the S out to get it in terms of a voltage from the other side, from the stator. And so we can divide the top and bottom by S, and you see here that we've divided the S out of my inductance, and we've also divided the S out of my resistance. So this equivalent resistance is going to be the rotor resistance divided by my slip speed. So now we can couple these two together into this transformer model. So this part over here is my stator, this part over here is my rotor. I'm going to take these two and I'm going to basically reflect them across here. Now, when I reflect them across the transformer to get rid of the transformer, you can see that my inductance and my resistance, so these become an LR prime and then a rotor prime. Now, these actual parameters we have to measure, so it doesn't really matter whether we're measuring an R or an R prime. So we took these pieces here, reflected them over. This is now the equivalent circuit of my induction motor. So we basically have the stator parts and we have the rotor parts that are reflected over. Okay, so now what we want to do is we want to take our combined circuit and we're going to take this rotor resistance here. So you see we're taking this rotor resistance here and we're breaking it up into 2 parts. Okay, so we want the rotor, the resistance without the slip. That's going to be related to my loss. So this is kind of the loss, the copper resistive loss in the rotor squirrel cage. And then everything else, the other part of it, is going to be related to my induced mechanical power. So what you see here is if I kind of divide these up, this was my combined piece here. We break it up into the base resistance and then this part, which is related to my induced power. Okay, so what we're going to do is we're going to say the power consumed in this resistor is related to my motor power. So that's my mechanical power produced by the motor, and then this is going to be my electrical power that's lost into heat. So like I said before, we get our torque by looking at powers rather than currents. So we're basically going to solve this circuit for power. So let's look at this. So what we have is we're going to start with our total power. So this is the total power of our circuit. We see that it has a square root of 3, okay? Because it has a square root of 3, because we're getting a line-to-line voltages and currents, and that's going to be divided by the square root of 3, and then we're going to multiply it for the 3 phases. Okay, so this is our total power. The first thing that we're going to do is we're going to lose some power in our stator copper. So that's going to be the power consumed in this resistor right here. Okay, or I guess you could do this one down here. So we're going to take our total power in, subtract off the stator copper loss. So that means that all of the power left, which is right here, is going to be all the power, what they call air gap power. So this is the amount of power that gets through the stator loss and across the air gap. Now we're going to lose a little bit of this power over in the rotor copper loss. So we're going to take that off. So now this point here, we now have our total mechanical power. Now we're going to take our total mechanical power, and this is a mechanical loss. Okay, so that's like our friction, all of that kind of stuff. You know, in the beginning video, it talked about how they put a fan. That's called windage loss. So that's the loss associated with the fan that's used to cool the motor. So all these mechanical losses, and then everything that gets over here is going to be equal to how much power our motor is supplying to our load. And the last piece, just as a review, this kind of wraps that up. But we also have the concept of regenerative braking. So for example, if our motor speed is greater than our synchronous speed, that means we're putting more torque, so our torque is kind of negative. So if our torque is negative, then all of our everything's going to get reversed, and we're putting torque into the system, and that means we're going to get current out of the system. So in regenerative braking, if we're putting in more torque, then we're going to get currents to flow back the other direction. And so then instead of taking power from our three-phase system, we're putting power into our three-phase system, and then our motor becomes a generator.